Astronomers have spent decades searching for a way to truly see another planet. Not a shadow, not a flicker of light, not a mathematical model on a screen. They wanted an actual picture, the kind of image a camera captures, showing a real world orbiting a real star. For most of history, that dream stayed just out of reach. Planets are small, stars are enormous and blinding. Trying to see a planet next to its star is like trying to spot a firefly next to a lighthouse from thousands of miles away. Then, one image changed everything. A faint point of light appeared in raw data collected by the James Webb Space Telescope. It was small, it was dim, but it was real. Scientists confirmed that this point of light was an actual planet, captured directly, sitting far from its parent star. For the first time using this telescope, humanity was not detecting a planet through indirect clues. Humanity was looking straight at one. This single image opened a door. Behind that door, researchers say, waited a series of discoveries stranger than anyone expected. Tonight we walk through that door together, one distant world at a time. This moment mattered more than a single pretty picture. For years, most exoplanets were confirmed using indirect methods. Scientists watched a star's light dim slightly as a planet passed in front of it. Or they measured a tiny wobble in a star's position caused by a planet's gravity. These methods work, but they never show you the planet itself. A direct image is different. It proves, beyond doubt, that a world is truly there. Researchers say this new image gave them something rare. A chance to study starlight that had actually passed through a planet's own atmosphere. That kind of light carries chemical secrets. It can reveal gases, temperatures, even clouds. Scientists suggest that once you can see a planet directly, you can start asking real questions about what it is made of. And once those questions started getting answered, the discoveries only grew stranger. The world captured in that historic image is called HIP 65426b. Researchers describe it as a giant gas planet, roughly 7 times the mass of Jupiter. It orbits its star at a distance far greater than anything in our own solar system, more than 100 times farther than Earth sits from the Sun. At first, scientists expected a fairly ordinary giant planet, hot, gaseous, and slowly cooling with age. Instead, the image revealed a planet sitting in a location that current planet formation models struggle to explain. According to standard theories, giant planets form inside a spinning disk of gas and dust surrounding a young star. That disk usually only reaches out to a certain distance before running out of material. HIP 65426b sits well beyond that expected boundary. Scientists suggest this raises an important question. How did a planet this massive end up so far from where it should have formed? Here is where the story shifts from strange to genuinely puzzling. When researchers studied the light coming from this planet more closely, they noticed something odd about its atmosphere. Instead of a smooth, predictable temperature pattern, the data showed uneven layers and shifting cloud structures. Some scientists describe this pattern as more chaotic than expected for a planet that simply formed and settled into a calm orbit. This unusual behavior led some researchers to propose a bold idea. Perhaps HIP 65426b did not form where we see it today. Some scientists suggest the planet may have formed closer to its star, then been pushed outward through gravitational interactions with other planets in the same system. Others propose an even more dramatic possibility. The planet may have been ejected from a completely different star system entirely, then later captured by its current star's gravity, becoming what astronomers sometimes call a wandering world that finally found a new home. There is a third idea some researchers find just as compelling. HIP 65426b might represent a case where planet formation itself works differently than assumed. Instead of always growing slowly inside a disk, some giant planets might form through a faster, more direct collapse of gas far out in the darkness surrounding a young star. If that theory holds up under more observation, our basic picture of how solar systems build themselves may need revision. None of these explanations are confirmed yet. Scientists are careful to point out that a single directly imaged planet cannot answer questions this large on its own. But researchers agree on one thing. This planet should not sit where it currently orbits, according to the rules we thought we understood. And that alone makes HIP 65426b one of the most important single images ever captured of another world. What makes this discovery even more significant is what it represents for the future. This was not just a picture of one strange planet. It was proof that direct imaging works, that this telescope can pull a planet's light apart from its star's glare and study it as its own object. Researchers say this success paved the way for pointing the telescope at other systems, hoping to capture similarly direct views of worlds only detected indirectly before. That success came sooner than many expected, because not far from this discovery, in an entirely different star system, scientists were about to encounter something that would spark one of the biggest debates in modern astronomy. The planet in question is called K2-18b. Long before Webb ever studied it, astronomers already knew a few basic facts. It orbits a small, cool star and sits within a distance often described as the habitable zone, the region where temperatures could allow liquid water to exist. It is also considerably larger than Earth, closer in size to a smaller version of Neptune. For years, K2-18b sat quietly on a list of interesting but unremarkable worlds. That changed once researchers pointed the telescope's instruments toward the light passing through its atmosphere. The first molecule they confirmed was water vapor, appearing clearly and repeatedly across multiple observations. That alone made the planet worth watching more closely, but scientists did not stop at water vapor. Further analysis revealed methane and carbon dioxide in the planet's atmosphere. Researchers say this combination suggested a thick envelope of hydrogen gas surrounding the planet, with the possibility of a deep layer of water or a global ocean sitting underneath that hydrogen blanket. Some scientists began referring to this type of world using a specific term, a Hycean planet, short for a hydrogen-rich world that may hide a vast ocean beneath its skies. Then came the detail that pushed this planet into international headlines. Researchers reported possible signs of a molecule called dimethyl sulfide. On Earth, this molecule is produced almost entirely by living organisms, especially marine plankton in our oceans. Finding a hint of this molecule on a distant planet immediately raised an enormous question. Could this be an early signal of biological activity somewhere other than Earth? Scientists were careful and remain careful about that possibility. The detection of dimethyl sulfide on K2-18b is still considered tentative. Researchers explain that the signal is weak and needs to be confirmed through additional observations before anyone can treat it as solid evidence. Non-biological chemical processes might also produce similar signals under conditions we do not fully understand yet. Extraordinary claims, scientists remind us, require extraordinarily strong evidence. Even with that caution in mind, the possibility alone changed how researchers talk about this planet. Some scientists describe K2-18b as one of the strongest current candidates for a world that might support some form of life, even if that life looks nothing like anything found on Earth. Picture a planet where sunlight barely reaches through a dense, hazy atmosphere. Picture an ocean stretching far below that haze, warmed just enough by starlight and internal heat to remain liquid across enormous stretches of time. Researchers suggest that if life exists there, it would likely be simple, microscopic, and adapted to conditions very different from our own oceans. There would be no need for sunlight to reach the surface the way it does on Earth, since any potential ecosystem could exist in darker, more stable layers below the visible atmosphere. What makes K2-18b so important is not that scientists have proven life exists there. They have not. What matters is that for the first time, researchers have a real planet with real measured chemistry that fits enough criteria to take the question seriously. Every future observation of this world will either strengthen or weaken that case, and astronomers around the world are now watching closely for the next round of data. While K218b captured attention for its possible biology, another nearby world reminded scientists that proximity alone does not guarantee answers. Proxima Centauri b holds a special place in the imagination of anyone curious about space travel. It orbits Proxima Centauri, the closest star to our own Sun, sitting only a little over 4 light-years away. In cosmic terms, that distance is practically next door. Since its discovery, this planet has been treated as the most likely first stop for any future mission beyond our solar system. Proxima b sits within its star's habitable zone, meaning temperatures there could theoretically allow liquid water. Naturally, scientists were eager to study its atmosphere using this telescope's sensitive instruments. Unfortunately, the results were disappointing in a very specific way. The planet orbits so close to its star that separating the planet's faint light from the star's overwhelming brightness proves extremely difficult. Researchers compare the challenge to trying to see a candle flame standing directly in front of a massive spotlight. Current instruments simply struggle to isolate the small amount of light coming from the planet itself. Beyond the technical challenge, there is a deeper concern about this world's habitability. Proxima Centauri is classified as a red dwarf star, and red dwarf stars are known for producing frequent, powerful flares. These flares release bursts of radiation that could strip away a planet's atmosphere over long periods of time, especially for a world orbiting as closely as Proxima b does. Scientists suggest that if Proxima b once had a thick atmosphere or surface water, repeated flare activity from its star may have slowly eroded that atmosphere away. Some researchers propose an even more specific possibility. Proxima b likely orbits with one side permanently facing its star. That means the planet may experience a harsh temperature divide, one hemisphere baked under constant starlight, and the other locked in permanent cold and darkness. If any habitable conditions exist there at all, researchers believe they would likely be confined to a narrow strip along the boundary between those two extremes, sometimes called a terminator zone. It would be a place of eternal twilight, neither fully day nor fully night, potentially the only region temperate enough to support any kind of stable environment. This creates a genuinely haunting situation. Proxima b is the closest potentially habitable planet we know of, close enough that a future spacecraft, traveling for decades rather than centuries, might one day reach it. And yet, right now, it remains one of the hardest nearby planets to actually study in detail. We can measure its size, its distance, and its orbit, but its true surface conditions, its real atmosphere, and any possibility of life there stay hidden behind the glare and violence of its own host star. Researchers see this as an important lesson. Being close to Earth does not automatically mean a planet is easy to understand. Sometimes the nearest mysteries are exactly the ones that stay hidden the longest, while planets trillions of miles farther away reveal their secrets more easily. Not every discovery from this telescope involves a possible ocean or a habitable zone. Some of the most important findings come from planets that are almost certainly lifeless, yet scientifically fascinating for entirely different reasons. WASP 39b is one of those planets. Researchers classify WASP 39b as a hot Jupiter, a large gas giant that orbits extremely close to its star. Because of that closeness, temperatures on this planet reach levels hot enough to vaporize many kinds of rock. Scientists expected its atmosphere to be relatively simple, dominated by a small handful of common gases stretched thin by extreme heat. Instead, the telescope's instruments revealed something far more complex. Researchers detected water vapor, sodium, potassium, carbon monoxide, and methane in the planet's atmosphere, all within a single system. That alone would be an unusually rich chemical signature, but scientists also found something they had never confirmed on another planet before: sulfur dioxide, a molecule created through chemical reactions triggered by intense radiation from the planet's star. This detection mattered enormously to researchers because it proved something theoretical for the first time. Scientists had long suspected that starlight could trigger chemical reactions in a planet's upper atmosphere, similar to how sunlight interacts with Earth's atmosphere to create our protective ozone layer. Confirming sulfur dioxide on WASP 39b gave researchers direct evidence that this kind of active atmospheric chemistry happens on other worlds, not just in theoretical models. Scientists describe this as photochemistry in action, meaning chemical reactions powered directly by light rather than heat alone. Finding clear evidence of this process on a planet so different from Earth suggested that similar chemical activity might be far more common across the galaxy than previously assumed. What surprised researchers even further were the exact ratios of these different molecules. The proportions did not neatly match any single existing model of planetary atmospheres. Some scientists describe WASP-39b's atmosphere as behaving like an active chemical laboratory, constantly producing reactions that current science cannot fully predict or explain yet. This shocking level of complexity forced many researchers to reconsider basic assumptions about extreme planets. A world too hot and too close to its star for life was still capable of producing atmospheric chemistry richer and more unpredictable than anything measured before this telescope's observations. Scientists suggest that if a blazing hot gas giant can surprise us this much, calmer, more Earth-like planets may hold chemical secrets we have not even thought to search for yet. WASP-39b taught researchers an important lesson before the next major disappointment arrived. Complexity and chemical richness do not require gentle conditions. Sometimes, the most extreme environments produce the most unexpected chemistry of all. Few exoplanet systems generated more excitement than TRAPPIST-1. This system contains 7 rocky, Earth-sized planets, all orbiting a small, cool star relatively close to our own solar system. Several of these planets orbit within the star's habitable zone, meaning temperatures there could theoretically support liquid water on a rocky surface. When this system was first discovered, many scientists described it as one of the best chances astronomers had ever found for detecting signs of life beyond our solar system. 7 planets, several potentially habitable, all conveniently close enough to study using upcoming telescope missions. Expectations climbed higher with each passing year, right up until this telescope finally turned its full attention toward the innermost planets. The results were far from what many researchers hoped to find. When scientists analyzed the light from TRAPPIST-1b and TRAPPIST-1c, the 2 innermost planets in the system, they found essentially no evidence of a substantial atmosphere. Not a thick blanket of gas, not even a thin, wispy layer clinging weakly to the surface. Just bare rock, exposed directly to space and to intense radiation from its host star. Researchers explain why this happened. TRAPPIST-1 is an ultra-cool dwarf star, and stars of this type tend to be far more active during their early history than stars like our Sun. Repeated bursts of radiation over billions of years likely stripped away any early atmosphere these inner planets once had, leaving behind sterile, airless worlds unable to trap heat or shield their surfaces. This finding hit particularly hard because TRAPPIST-1 had been treated almost like a symbol of hope within the search for habitable worlds. Scientists describe the loss of that optimism as a genuinely crushing moment for the field. A reminder that a system can look perfect on paper, with the right-sized planets in the right orbital distance, and still turn out to be lifeless in reality. Researchers stress that this does not necessarily rule out the entire system. TRAPPIST-1 still contains additional planets farther from the star that have not yet been fully studied, and some scientists hold on to cautious hope that outer planets in this same system might have retained thicker atmospheres, since they receive less direct radiation from their star. Observations of those remaining worlds continue, and researchers say final conclusions about the whole system remain incomplete. Even so, the early results forced a broader reconsideration within the scientific community. Habitability, researchers now emphasize, depends on far more than simply sitting at the right distance from a star. A planet's fate is also shaped by the behavior of its star across billions of years, something far harder to predict or observe directly. TRAPPIST-1 taught scientists that promising conditions on paper do not guarantee a living world in practice, and that lesson now shapes how researchers evaluate every new candidate for a habitable planet. Taken together, these discoveries paint a strange and unsettling picture of our galaxy. This telescope has now studied dozens of distant worlds, revealing oceans that might hide beneath thick hydrogen skies, giant planets sitting in places current theories say they should not exist, chemical laboratories operating inside furnace-hot atmospheres, and rocky worlds stripped completely bare by their own stars. And yet, across all of these discoveries, one specific thing remains missing. No planet studied so far has produced a confirmed, undeniable signal of life. Scientists have found intriguing possibilities, promising chemistry, and tantalizing molecules that might hint at biology. But nothing yet meets the strict standard required to declare, with confidence, that we have found life beyond Earth. Researchers describe this gap as one of the more puzzling aspects of modern astronomy. Based purely on statistics, with billions of planets estimated to exist across our galaxy alone, many scientists expected signs of life to appear more readily once telescopes powerful enough to search for them became available. Instead, the search has revealed abundance without confirmation, countless planets, but so far, only silence when it comes to biology. Some researchers suggest this silence simply reflects how difficult the search remains, even with advanced instruments. Detecting a biosignature molecule from light years away requires extremely precise measurements, and confirming that signal beyond doubt takes multiple observations and considerable time. Other scientists propose a more sobering possibility, that life, in any form we would recognize, may simply be far rarer across the universe than earlier optimism assumed. There is also a third possibility that some researchers find intriguing. Perhaps life exists in forms different enough from Earth's biology that our current search methods are not designed to detect it properly. If alien life relies on chemistry very different from carbon-based biology, or exists in environments researchers have not yet considered searching, current techniques might simply be looking in the wrong places. Whatever the true explanation turns out to be, this research has already reshaped how scientists approach the search for life. Every new discovery, even ones that end in disappointment like TRAPPIST-1's bare inner planets, sharpens the tools and expectations used for the next candidate world. Researchers describe this ongoing process as building toward eventual answers. One observation, one planet, one spectrum of light at a time. Looking back across every discovery made possible by that first direct image, one truth stands out clearly. The universe has proven far stranger and far more varied than most scientists predicted even a decade ago. We have seen a giant planet sitting where formation theories say it should not be able to exist. We have seen a possible ocean world hiding beneath a thick hydrogen sky, carrying a chemical signal researchers are still working to confirm. We have watched a nearby, tempting world stay hidden behind the glare of its own star. We have found extreme chemistry thriving inside a furnace-hot atmosphere. And we have watched genuine hope fade into disappointment as a beloved system of 7 worlds revealed bare, airless rock instead of thriving planets. None of these discoveries have given researchers a final, confirmed answer to the biggest question driving this entire search. But together, they have given scientists something almost as valuable: a clearer map of where to look next, and a better understanding of just how complicated that search truly is. Every one of these worlds started as a single point of light, captured because a telescope finally became powerful enough to see it clearly. Somewhere among the next set of images, spectra, and measurements, researchers may finally find the evidence that answers humanity's oldest question about whether we share this universe with anyone else. And until that day comes, every faint point of light still deserves a closer look.